of my brain. Okay, recording has started, so good morning everybody and welcome back to Math 115. Today we're going to continue our conversation about the unit circle and about trigonometric functions. Okay, so what I'm going to do is I'm going to go back through some of the stuff we did last time just to remind ourselves of how we got to where we are now. And then I'm going to give a bit of a different take on the unit circle, which is a little bit more intuitive than the sort of very mathematical way that I wrote down this definition of this function p of theta. I think didn't land super well. So I'm going to go back and I'm going to talk a little bit more about the unit circle, and then we'll move on to some new trigonometric functions, and we'll practice computing trigonometric functions, and we'll practice some other examples just working with the unit circle, finding points on the unit circle. We'll cover this cool looking picture, and then yeah, more unit circle stuff. So that's what we're going to do today. So first, let me remind us where we came from. And where we came from is we started basically this entire unit circle business by first trying to understand what is an angle. Okay, and we decided that an angle was going to be a measurement, some kind of measurement in the difference in direction between two rays. So if you're thinking about a clock, you can think about the difference in, well, the minute hand is pointing at 12 and the hour hand is pointing at 3. So the difference between them would be like, I don't know, 3 hours, right? So you could say that this angle, you could measure this angle as 3 hours if you want, or you could measure it as 45 degrees, or you could measure it as pi over 4 radians. Okay, all just different ways of saying, of explaining the difference in direction between two rays, which we're taking our minute hand and our hour hand to be the rays here. Okay, so we had two different types of measurement for angles, and those were degrees and radians. We said a degree is 1/360th of a full revolution, so it's pretty small. We have to do it 360 times in order to go all the way around in a circle. And we covered right angles, acute angles, obtuse angles. And then we had these radians, right? And radians were just a different way of measuring angles, okay? Kind of like how we have feet and meters, okay? We have different ways of measuring angles. And radians were defined in a clever way. They were defined in a way such that if you put an angle of 1 radian at the center of the unit circle, then the arc length produced, which is this length here highlighted in green, is the arc length, okay, kind of our pizza crust on our pizza slice, will have length 1. Okay, so 1 radian gives an arc length of 1. Okay, so then we talked a bunch more about angles and how to convert between them. Excuse me. And let's see. Then last time we talked about this example where we had this kind of clever problem here where we had to find the arc length on a circle that didn't have radius 1. All we had to do was use a sort of a proportionality argument here. And then we kind of started to talk about the unit circle, and the preview or the preliminary thing that we needed to know to talk about the unit circle was a review of how triangles work. Okay, so first of all, the angles inside a triangle add up to 180 degrees. or if you're talking about in radians, then they sum up to pi. And we have the Pythagorean theorem, which tells us that if we have a right angle, okay, then this length of the hypotenuse is given by the square root of the sum of the squares of the other two sides' lengths. So that was the Pythagorean theorem. And the Pythagorean theorem sort of then gives us two special right triangles for which we can always find the lengths of the other three sides if we know the length of just one side. Okay, because all of the side lengths are proportional according to the proportion scheme which fits that given special right triangle. So the proportion scheme for the 45, 45, 90 triangle was that the two side lengths, which are opposite the 45-degree angles, will have the same length. And then whatever length that is, we take it and we multiply by square root 2 to get the length of the hypotenuse. So in this example, we were given the length of the hypotenuse. So to find the length of these legs, we had to take that length and divide by square root 2. So that's about a 45, 45, 90 triangle. And we also had a 30, 60, 90 triangle, which had another kind of nice proportion scheme, which was that the smallest side, which remember the smallest side is always across from the smallest angle. Smallest side had length x, well then the other sides will have length x times the square root of 3, and then 2x will be across from the 90-degree angle. Okay, so smallest angle goes to the smallest side length, the medium angle goes to the medium side length, and the large 90-degree angle goes to the longest side. Okay, so then we define the unit circle. And let me just say that all of this time that we're going to work on trig in the unit circle, this is really the background for which everything is always the same, okay? So anytime we're working on a trigonometric function or an angle, okay, we want to be thinking that this unit circle is like the paper on which we're going to do our work, okay? This is just like the background, and it's just always here, and we can use certain properties of it to our advantage. Okay, so we really want to remember that this is its formula, okay? So in particular, any point which is on the unit circle will satisfy this equation if we plug x comma y in for x and y in that equation. We should get 1. Okay, so that's its equation. Its center is at 0, 0, and the other important property that we have about the unit circle is it has radius 1, which means that if I measure the length of any line segment which goes from the center of the circle to the outside of the circle, this has length 1. Okay? Likewise, if I draw another one that goes from the center out over here, or I don't know, even make it like this. Okay, this line segment also has length 1. Okay, this line segment has length 1. Okay. So here is how we're going to think about trigonometric functions. And this is the sort of intuitive understanding of the trigonometric system. Okay? Our goal with trigonometry is to somehow, what is the word? Reconcile the following two ways of understanding where a point is on the unit circle. So say that I start right here. Okay, I start at the center of the unit circle. Okay, and this is like a top-down view of a map, and I'm standing here and I'm going to walk somewhere. The place I want to walk to is some point which is on the unit circle. I'm going to choose this random point here, but we could choose it over here or down in here or over here, really anywhere on the unit circle. Okay, and I ask my two best friends how to get from where I start to where I want to end. Friend 1 says the following. Walk x units to the right, then walk y units up. Okay, so friend 1 tells me to do that. So what do? I just walk along here, da 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 da. And then I walk, so that was x units to the right, and then I walk y units up. And that's a valid set of directions for how to get to that point from where I started. Okay, I can just walk x units to the right, and then I walk y units up. And then he says, well, then after that, you'll be at the point x comma y. Okay, perfectly valid way of thinking. And this is how we're used to understanding locations in the Cartesian plane. We say, well, a location in the Cartesian plane is just basically the set of directions for which you walk x units left or right and then y units up or down. That's how we understand locations in the Cartesian plane. But there is another way of understanding this. Okay, so friend 2 is sort of like clever. Friend 2 says, well, that sounds like too much walking to me. Instead, just point yourself in the direction theta. And then walk straight 1 unit. Okay, so we just point ourselves in the direction theta and we walk straight. So rather than taking this silly route, okay, what I'm going to do is, okay, originally I was going to start facing in this direction. So here's my eyeballs. Okay, and I'm facing in this direction and I walk this way, and then I turn so that I'm facing in this direction, and then I walk y units in that direction. Okay, that's the original process. The new process is first to turn the orientation of my body. Let me get rid of this. Like that. To turn the orientation of my body by theta degrees, or theta radians. And then, once I'm turned, I'm just going to walk straight. And I'm going to walk 1 unit. 1 unit. To get to where I want to be. Okay, so rather than walking right and then up, I'm going to walk diagonally. Okay, I'm going to start facing in this direction. So I start by first changing the direction that I'm looking, and then I walk straight in that direction for the entirety of my trip. Okay, so this is kind of like, if you jaywalk, you can get from where you are to where you want to be faster than if you walk all the way to the crosswalk and then walk across the crosswalk. Okay, that's kind of what this is about. So our goal here is to develop a relationship between the directions, which these directions can kind of be nicely packaged as the directions x comma y. And we just know when we see this, this means walk x units to the right or left and then y units up or down. We want to reconcile these set of directions with the new set of directions, which are the set of directions theta comma 1. Okay, and the way we read this set of directions is turn yourself theta degrees and then walk 1 unit away in that direction. So we want to develop a relationship between the set of directions, which is turn yourself theta degrees and walk 1 unit, and the set of directions, which is walk x units to the right and y units up and down. This is what we want to understand. Now, since we are always working on the unit circle, okay? Since we're always working on the unit circle, friend 2 doesn't even really need to specify that we walk straight 1 unit. Okay, and why is that? Well, the reason is no matter which direction I'm looking, if I walk 1 unit away, I'm going to be on the unit circle. If I walk further away, then I'll be off the unit circle. And if I walk less far away, then I won't be on the unit circle either. I want to be on the unit circle. So no matter which direction I pick, I need to walk exactly 1 unit, or else I'm not even going to be on the unit circle. And our goal is to give directions to a point on the unit circle. So this and walk straight 1 unit is sort of implied by the fact that we want to end up on the unit circle. So we can actually omit this part, and we can omit the 1 here, and we can instead just say, turn yourself theta degrees and then go until you hit the edge of the unit circle. So the only direction that friend 2 really needs to give me in order for me to get to this point on the unit circle is actually just, well, in which direction should I start facing? And then I know, because I want to end up on the unit circle, that I need to walk 1 unit in that direction. Okay, so really the relationship here should be between x comma y and theta. Okay, so friend 2's directions are somehow a little bit more simple because all they have to tell us is which direction should I start off in. And I know, just because I know I'm working with the unit circle, that I need to go 1 unit to get there. Okay, so that's kind of what we're trying to reconcile here. We're trying to find if friend 2 gives me the directions to turn theta degrees and then walk 1 unit, can I formulate the instructions that friend 1 would have given me in order to get to that point? And likewise, if friend 1 gives me these complicated directions x comma y, can I find the angle theta which will allow friend 2 to give me these more simplified instructions? Okay, so this is the relationship that we want to understand, is what is the difference between these 2 sets of directions? So how do we go from understanding directions in terms of an angle and understand those directions in terms of a point x comma y, and how do we do the opposite? That is our business with the unit circle. Okay, so that is what this was saying, which I feel like didn't totally land. So let me go back through it and explain what this says. This says let p of theta, so some function p of theta equals x comma y, be the point x comma y on the unit circle, which lies on the terminal side of the angle theta measured from the positive x-axis. So what does this say? This says that if I take theta and I plug it into p, okay, I take the directions that friend 1 gives me and I plug them into this function p, and it, goes beep boop bop, and then out pops x comma y, the directions that friend 1 was going to give us. Okay, so that's what p does. And likewise, we can think of the fact that, well, theta will also be equal to the inverse of p of x comma y. Okay, if x comma y is on the unit circle, then p inverse will give us theta. Okay, so this is just to describe this function p basically converts the directions from method 1 to method 2 and vice versa. Okay? And then here's what we learned. This is messy, so I'm going to clean this up. Okay, so oops, I want to get rid of that. Here's what we learned was the following. We have that p of theta is equal to x comma y. And this is sort of not great in terms of a function because it does the following. It takes an input of one number and it gives us an output of two numbers, which is not the best. We'd rather have a function which takes an input of one number and outputs one number. So what we do is we kind of split p of theta into two functions. We say, let's have a function sine, which takes my directions in terms of theta, and it will give us just the part of the second form of directions, which tells us how far up and down to go. And then cosine theta will take this angle, and it will give us the part of directions which tell us how far left and right to go. That is what cosine theta and sine theta do. So if we have our unit circle here, okay, and we are given x comma y, then what this is saying is that y is equal to sine of theta and x is equal to cosine of theta. Okay, so cosine theta tells us, given an angle, and I want to get to this point right here, I should walk cosine theta units to the right or left. And sine theta tells us about how far up and down we should go to get to those points. Okay? So if we have a unit circle, we can describe any point on it as the point on the unit circle as the point cosine theta comma sine theta, where theta is the angle measurement from the x-axis here. So this is telling you exactly what the relationship is between theta and x comma y. We have x comma y is equal to cosine theta sine theta. Okay, let me pause for questions. Is this making a bit more sense when I've kind of framed it in this new way? So much better. Okay, good. Anybody else have comments or questions? Do we like the new intuitive approach better than the mathematical approach? Okay. Well, let me say this, okay? We're going to move forward from this eventually, and we're going to talk about, lots of trig functions, and really the basis of our entire discussion about trigonometry, which we're going to talk about for like the next month, is going to be entirely predicated on your understanding of this unit circle. So I really don't mind slowing down and taking more time to go over this unit circle to make sure that everybody in the class has a good understanding of how this is sort of working. Because once we start talking about cotangent, tangent, and all these different trig functions, it's going to be sort of implicitly assumed that we have a working knowledge of how the unit circle works and what is the relationship between theta and this point x comma y. So I guess please tell me if you're confused by this stuff, because I don't mind going back and explaining it again, and I don't mind clearing up any parts that have been sort of confusing. And if you don't feel comfortable asking in class, then please email me or put it on your exit slip, or somehow let me know using the anonymous survey or something, so that I know that there are students in the class who need a little more help with this, and that's fine if you do. Okay, shall we move on, or more discussion about the unit circle? Okay, I'm not seeing anything, so I'm gonna start moving on now. Okay, so let me maybe go back through this example. Okay, I'm gonna go back through this example. So let's find out what are sine of pi over 4 and cosine of pi over 4. Okay, and I'm going to use these definitions. The definition says that this number sine of pi over 4 will be the y-coordinate on the unit circle, which corresponds to the angle theta, which in our case is pi over 4. Okay, so let's first draw our unit circle. And our unit circle should definitely have the angle pi over 4, which, remember, pi over 4 radians equals pi over 4 times 180 over pi degrees, which is equal to 45 degrees. Oops, I don't need to write degrees if I put the symbol. So 45-degree angle. I measure it from my initial side, which is always the positive x-axis. So here's my initial side, and I measure 45 degrees. I know 45 degrees is half of a right angle, so it's going to go like right here. Okay, and now I'm interested in what is this point, this pink point. I want to know what is that point. I know this point has coordinates cosine of pi over 4, comma, sine of pi over 4. And I want to know what these two numbers are. I want to know what these two numbers are. And the information I'm given is that this angle is theta, or this angle is actually pi over 4. So I know that this angle is pi over 4, and I know that this length is 1. And I want to use that information to figure out what is cosine pi over 4 and what is sine of pi over 4. So what I do is visualize the directions of friend number 2. And I'm running out of colors here. Maybe I'll use, I don't even know. Maybe I'll use green, is kind of similar. Orange, how about orange? Okay, so I know that friend number 2 would give me directions in the following way. They would say you should walk cosine pi over 4 units to the right. And then they would say you should walk, after that, you should walk sine of pi over 4 units up. So what I'm going to do is I'm just going to fill in the sides of this triangle, okay? I'm going to fill in the sides of this triangle. And I know because this is a vertical line, right? On the part where I'm just walking straight up and down, it's a vertical line. And I know that a vertical line and a horizontal line form a right angle at the base. So this angle right here is a right angle. And now, if I want to know what the length of this side is, and if I want to know what the length of this side is, I've got a triangle here with a right angle. And I know one of the angles inside the triangle is pi over 4, so I can figure out what the other one is. So this angle inside was 45 degrees. Oops, that was too much. This angle inside was 45 degrees. So if I have a 45-degree angle and a 90-degree angle, I know that the other angle also has to be 45 degrees. And so if I want to know what the length of the other two sides are, I need to use the proportions, which said, okay, so this triangle, if I bring it out, looks like the following. We got 45, 45, 90, and this has side length 1. Okay, and if I were to compare this to the 45, 45, 90 triangle, which I had before, I know that the side lengths of the 45, 45, 90 triangle will be x and x and x times the square root of 2. So here I know what x times the square root of 2 is. It's 1. And I want to know what is x. So I just set x square root of 2 to be equal to 1. And then I just divide both sides by the square root of 2. So I get 1 over the square root of 2. And then I would rationalize that denominator by multiplying by 1. And I would get square root of 2 over, well, the square root of 2 squared would be 2. Okay, so I get square root of 2 over 2 is what these side lengths are. So I can fill them in now. This one's square root of 2 over 2, and this one's square root of 2 over 2. And if I look back at the unit circle, I realize that those numbers, the square root of 2 over 2 is going to correspond to the number sine of pi over 4. And likewise, square root of 2 over 2 is going to correspond to the number cosine of pi over 4. So my goal was to find out what number sine of pi over 4 and cosine of pi over 4 represent. And they both represent square root of 2 over 2 in this case. Okay, but that was very dependent on the angle that we chose. The angle which was in our triangle here happens to be 45, so we could figure out what the side lengths were quite easily using a 45, 45, 90 triangle. Okay, so this is how we actually define the values which the function sine takes given a certain input. Okay, so we give it an input in terms of an angle, and it gives us an output, which is in terms of a coordinate. And that coordinate is, for the sine function, it's the y-coordinate of the point on the unit circle, which corresponds to the angle which was originally given. And likewise, cosine will give us the coordinate. That's right, Sam. Both cosine of pi over 4 and sine of pi over 4 are equal to square root 2 over 2. Okay, so let's do one more example. Well, let me finish what I was saying before. Basically, what I was saying before is that these things, these numbers are defined by, you take a look at the angle inside, you put it in the unit circle, and then you find out what is the y-coordinate of the point on the unit circle which corresponds to that angle, and that is how we define what is the number sine of pi over 4. Okay? And this is a function, right? So we can also imagine taking an inverse of this function, which it'll turn out this function does have an inverse for certain values of x. And if we do something like sine inverse of square root of 2 over 2, this is like you take the point on the x on the unit circle which has a y-coordinate square root 2 over 2. Okay, there's only one of them. Well, actually, there's two of them. And then this is going to be equal to pi over 4. It's going to spit back out the angle which produces that y-coordinate. Okay, so we're going to have this relationship later on, but we'll think more about that later. I don't want to confuse you guys about that so far. So this sine and cosine function really give us an understanding of the relationship between an angle and the point on the unit circle. So if we had a calculator button that would tell us what is cosine of pi over 4, well, we could use that calculator button to take any angle, and then we would just know the x-coordinate of the point on the unit circle, which would correspond to that. Okay, so these functions are really useful functions. So let's do one more example. Let's find sine of 30 degrees and cosine of 30 degrees. Okay, I'm just going to go through this example a little bit quicker than I did the last one. Okay, the first step is always to draw my unit circle. Of course, I want to actually have a straight line. Well, that was pretty good. Almost got it perfectly on. Okay, so there's our unit circle. Okay, and what does 30 degrees look like? Well, 30 degrees is 1/3 of 90 degrees. So I want to draw an angle in here which looks like 1/3 of 90 degrees. So I'll draw my initial side goes out to the right. And 1/3 of 90 degrees is going to look like, well, here's half of 90 degrees. So 1/3 is maybe down here. And our question is, what are the coordinates of this point here? Okay, and here's what I do. I use the fact that this is a 30-degree angle. Then I drop a line here which goes straight down. and I make a right angle, and I know that the hypotenuse of this triangle is 1. So if I were to bring this out, I would have a triangle. This triangle has a right angle here, a 30-degree angle here, a hypotenuse whose length is 1. And what should this angle be right here? In the top right corner, what should that angle be if the other ones are 30 and 90? That's right. If we want to find out what it is, we can do it easily. We know the angles inside a triangle should add up to 180, and I've already used up 90, and I've already used up 30. So 180 minus 120 is 60. So that's what should go right here. So I have a 30, 60, 90 triangle, and I know one of the side lengths. So guess what? I can use the same principles that I was using before and compare this triangle to the one that we had before. The one we had before said that if the length of the side which is across from the 30 is x, then the length which is across from the 60 will be x times the square root of 3, and the length which is across from the 90 will be 2 times x. So in our case, we have that the hypotenuse 1 is equal to 2 times x. So I know that 1 is equal to 2 times x, and therefore x is equal to 1. So if I want to fill in what is the side length here on our actual, what is this side length here? Well, all I would do is I would take x, which I know to be 1. So this length, oh, what am I doing? 1/2. 1/2 here. So this will be a 1/2. And the other side length will be 1/2 times the square root of 3. In other words, square root of 3 over 2. So this is how I find these side lengths. So if these are the side lengths of this triangle, then the point x comma y is equal to the point, well, we look at the x-coordinate, that's how far left and right we should walk. Well, we should walk to the right square root 3 over 2 units. So we get square root 3 over 2. And then how far up and down should we walk? Well, the side length across from the 30 is 1/2. And that tells us how far up and down we should go. So we get this point, 3/2, comma 1/2. And remember, we said that sine of 30 degrees will be equal to the y-coordinate, and cosine of 30 degrees will be equal to the x-coordinate. So to wrap this example up, we can say that sine of 30 degrees is equal to, well, we just look at the y-coordinate, it's 1/2. And cosine of 30 degrees is equal to square root 3 over 2. Okay? Yeah, x was 1/2, Sam. Thanks for catching that. Okay, so let me get some ratings in the chat, okay? Out of 10, I'd like you to rate how comfortable you feel with this example we just did. So 1 is totally not comfortable, I want to see more examples. And 10 is, this makes sense to me, I could produce this on my own. Okay, mostly in the upper range, so that's good. Yeah, again, with this stuff, you know, it really just takes practice. Really just takes practice. Okay, one thing that I do want you guys to remember, by the way, is that our vertical line, our dotted line, should always be vertical. Okay, so I don't want to see anybody doing this, dropping this guy over here. That's going to produce a really difficult situation for you. Okay, so we want to instead, we want our vertical line to, or our dotted line to always be vertical. Okay, so if our point is down here, well, we draw our angle, and then we drop our vertical line would go to the x-axis. Okay, that's how we would do that one. Okay, all right, I'm going to move on now and talk about other trigonometric functions. Okay, so we have 4 more important ones, okay, which are as follows. Okay, tangent of theta. Okay, tangent of theta is equal to sine of theta divided by cosine of theta. Okay, and it gives us the value y over x. And if you're wondering why it's called the tangent, I'll give you a picture to explain why. We have a unit circle here, and we have a point here, x comma y. Then the tangent function describes the length of the line, which is tangent to this circle, and it describes the length of the line which is tangent to the circle until it touches the x-axis. So just imagine that it touches right here. Then this length here is tan theta, if this is theta. Okay, so that's why it's called tangent. A tangent line is a line which comes close to our circle and touches it at one point and then goes on forever away. Okay, that's what a tangent line is. So if we take our tangent line and we measure the distance between the point where it intersects our circle and the point where it intersects the x-axis, that's what the tangent line, or the tangent function, will give us. Okay, and it's given by taking sine theta divided by cosine theta, so we just do y over x. Okay, now these next two are confusing. Here's why. This one, we call this the cosecant, and we call this one the secant. Okay, and what's going to be confusing is the fact that cosecant is 1 over sine, and secant is 1 over cosine. Okay, so you can imagine why that's confusing, because the cosecant does not go with the cosine. Okay, we have cosecant goes with sine theta. Okay, so it's 1 over sine theta. And I always just remember these because they're the opposite of what I think they should be. Okay, so I just think cosecant, well, I would imagine that would go with cosine, but I know that it should be the opposite of what I think, so I think it should be with sine. Okay, so cosecant theta is just given by taking 1 and divide it by the value sine theta, which, remember, since sine theta was always equal to the y-coordinate of that point on the unit circle, we can just do 1 divided by y to get cosecant, 1 divided by x to get cosecant, and then to get cotangent, we just do sort of the reciprocal of tangent. Okay, so tangent gives us y over x. To do cotangent, we just do x over y. Okay. If you want to know how cotangent manifests, let me not say how cotangent manifests. I don't remember. Maybe I'll look it up and I'll give you a cool drawing. Anyways, these last three, you basically find them by figuring out first what is sine, cosine, and tangent, and then you just flip those guys in order to get cosecant, secant, and cotangent, respectively. Okay, question in the chat, which I didn't recognize. How did I get square root 3/2? Okay, so let me go back and explain that for Sam. So Sam, here we found that since 2x was equal to 1, we set 2x equal to 1, and then we found that x was equal to 1/2. So if I know that x is equal to 1/2 here on a 30, 60, 90 triangle, what I should do to get the side length, which is across from the 60, is I should take x and multiply by the square root of 3. So in our case, x was 1/2, and then I take that and I multiply by the square root of 3, which I can think of the square root of 3 as square root 3/1, and then I multiply straight across. So 1 times the square root of 3 is square root of 3, and then 2 times 1 is 2. Does that clear things up? Yeah, okay, cool. Yep, I just multiplied. Okay, so now that we have all these other trig functions, let's do another practice example. Okay, we want to find the value of each trigonometric function when theta is equal to pi/2, if it exists. And from the way that this question is worded, we should already be thinking, well, maybe some of these are not going to exist for some reason or another. Okay, so let's figure this out together. So we want to do all 6 trig functions. So each means sine, cosine, tangent, cosecant, secant, cotangent. So let's draw our unit circle. I'll draw it with white. I'm not one of those instructors that can draw a perfect circle, but I can use the iPad. Okay, so theta is equal to pi/2. Someone tell me, what kind of angle is this? What kind of angle is pi/2? Somebody immediately recognize what that's going to produce? Yeah, 90-degree angle. Anybody remember the word we had for a 90-degree angle? We had a special word for 90-degree angles. Yeah, right angles. So our angle here is the angle which goes 90 degrees, and we would put a little box here. Okay. So all of these values of these trig functions are going to depend on the coordinates of the point on the unit circle which this angle would produce. So what is this point x comma y? Does anybody know immediately what this point should be? You're close. 1, 1 would say 1 comma 1 would say go to the right 1 and then up 1, and we would get here. Yeah, I think we should have 0 comma 1. We don't move left or right at all, so we just say 0, okay? So if friend 2 was going to give me instructions and they wanted to tell me how far left and right and how far up and down I should go, well, I should not go left or right at all. I should just go up 1 unit. So this is the point 0 comma 1. Okay, so we have x equals 0, y equals 1. And now I'm just going to go through all of these different trig functions. We said that sine of x, or sine of theta, would be equal to the y coordinate, which in our case is equal to 1. We said that cosine of theta would be equal to the x coordinate, which would be equal to 0. Now we said that tangent of theta, we said that one was just equal to sine of theta divided by cosine of theta. In other words, it was equal to y over x. And what's that equal? 1 over 0. So, big problem here. We're trying to divide something by 0. So it turns out tangent of pi over 2 is undefined. Okay, so those are our 3 main ones. We like sine, cosine, and tangent the best. We've also got our other trickier ones. We'll do those ones in orange. Remember, we have cosecant of theta. This should be equal to, well, I know cosecant. I wish it went with cosine, but I know it doesn't. It goes with the opposite of what I would think it goes with. So I know that cosecant is equal to 1 over sine theta, because all is wrong with the world. And that's just going to be 1 divided by, well, I know sine theta is y, so I put y here. And I know what y is, it's 1, so I get 1 over 1 is equal to 1. Then we get secant theta. I almost said cosecant again. That's just how confusing this is. Well, I know the secant theta, I would imagine that the s goes with the s, but sorry, the s actually goes with the c. So we get 1 over cosine theta. And that would be equal to 1 over, well, I know cosine theta is equal to the x coordinate, so I'm going to put an x here. And I know that x in our case is equal to 0, so this is 1 over, this is 1 over 0. And that's equal to undefined. Well, it's not defined. It's not equal to anything. Okay, so we got another undefined result here. Okay, and finally we have cotangent of theta. And one might imagine, well, we already know tangent theta doesn't even exist, so maybe this one's just undefined. What do we think? Do we agree or disagree? Disagree. Anyone else want to weigh in? Also disagree. Yeah, I kind of asked it in a way that makes it seem like disagree is the answer, huh? Okay, so my point here is you're right. We can do cotangent of theta because I didn't define cotangent of theta to be 1 over tan theta. Okay? I did not say that cotangent of theta is just 1 over tan theta. This will be true if big if tangent of theta exists. But in our case, tangent of theta doesn't exist. So we have to use the actual definition of cotangent. So the actual definition of cotangent, oh, well, I did put it here. So I should have put if it exists. But the real definition of cotangent is x over y. Okay, so in our case, it's just going to be equal to 0. Equals x over y is equal to 0. So it's fine for us to do that. So you'll notice, okay, there is a relationship between these functions here, okay? Cosine theta was 0, and that caused secant theta to not exist because we would do 1 over cosine theta. Likewise, we have sine of theta is just equal to 1. So when we do 1 over sine theta, we get 1 again. Okay, so all these functions are all sort of related to one another, okay? Sine and cosine are the most important, and then we get everything else just from manipulating those two, okay? We either divide them, or we take one as a reciprocal, or we take the other one as a reciprocal, or we divide them in a different way. Okay? Another way you can think about cotangent would be to say it's equal to cosine of theta divided by sine theta. All right. Any questions about this problem we did here? Okay, so now we have an idea of how we find all six trigonometric functions. Okay, using all of these definitions. Okay, so by the way, you'll notice I didn't draw a triangle here. Here's why. If I were to take some angle theta like this, I can draw a triangle, right? And as I draw more and more triangles moving up, right, what happens to my triangle? It becomes skinnier and skinnier to the point where my triangle is like so thin that it's barely even a triangle anymore. And as this angle comes all the way up to pi over 2, this triangle sort of collapses on itself. So I think maybe I can visualize this somehow. So if I have like basically a triangle, and if I imagine this side length being like, why does it do that to me? If I imagine this side length like coming closer and closer and closer and closer and closer until it's actually all the way on top of it, then it's not even really a triangle anymore. Okay, so that's where our triangle went. But in some sense, this is even easier because we didn't even have to use a triangle to figure out what the point on the unit circle was. We know since we just go straight up and we should go 1 unit, well, that in this case, the directions are basically the same between friend 1 and friend 2. Friend 1 says, okay, turn your body so you're facing north and then walk 1 unit. And then friend 2 says, walk 1 unit north. They're kind of the same. All right. Let's find the point on the unit circle corresponding to, I'm going to modify this equation. Rather than 2 pi over 3, we're going to do something cooler. We're going to find the point on the unit circle which corresponds to negative 2 pi over 3. That'll be more fun, I think. Okay, so let's have a unit circle as always. This is like our constant, right? This is like the paper which we're going to do our math on, okay? And the paper is always the same. We want to make sure the paper is the same every time. Okay, and now what we're going to do is we're going to try to draw the angle. Negative 2 pi over 3. Well, I can think about this in the following ways. Well, 2 pi over 3 is a negative angle. And I know that pi is half a revolution. So I should do like 2/3 of a negative revolution, of a negative of a half of a revolution. So this whole angle from here to here would be negative pi. Okay, if we had an angle which was just like straight across like this, that angle would be negative pi. So I'm just going to do negative 2/3 of that. Would be something like, well, I would start here going to the right as my initial side, and then I would go like 2/3 of the way. No, 2/3 of the way would be more like this. Two-thirds of the way to negative pi. Okay, so I could think about it like that, or I could try to translate it. I could say negative 2 pi over 3 times 180 divided by pi would be 360 over 3. Negative 360 over 3 is equal to negative 120. And I know negative 120 is like negative 90 would be a right angle, and then I would go an additional negative 30 to get to negative 120. So I could think about this instead as, okay, we do one right angle and then we go an additional 30 degrees. That's another way you could think about it. Okay, how you draw this is up to you. After a while, you may not be super comfortable working with radians at this point, but after a while, you might start to get the hang of it and you recognize, well, I know halfway around the circle is pi, so negative 2/3 is like almost halfway around the circle in a negative direction. Okay, so we're supposed to find the point on the unit circle which corresponds to this angle theta. This angle is negative 2 pi over 3. So I'm interested in finding out what are the coordinates of this point right here, x comma y. Okay, and here's how I'm going to do it. I'm going to use a triangle again. Most of the time we use a triangle. And to form my triangle, okay, I'm going to draw in a dotted line. Okay, going to draw in a dotted line in order to form this triangle. And I want everyone to remember, you know what, I actually realized I have this other cool thing. I can even do this. Watch this. Oh, nice. Okay, so if I have this dotted line, then the dotted line, oof, I don't like that. Dotted line is always vertical. Okay, so when I draw my dotted line in here, it's going to look like this. Okay, can it straighten the dotted line though? Because that would be cool. Oh, it can. Wow. That's not very good though. Ooh, that looks nice. Wow, I'm thrilled. Okay, so here we have a right angle. Okay, so our dotted line is always vertical, and we have now basically a triangle. Okay, and now I'm going to copy this triangle down. I'm going to try to think about it in the following way. Something like this. The right angle here. And I know that this side length here is 1. And now here's my question to you all. What angle measure is produced in this green region? Yeah, 60, right? Because this was 120, and I know that all the way is 180. So 180 minus 120 is equal to 60. So I know that this angle in this region here should be 60 degrees. Okay? And then I have a 60-degree angle and a 90-degree angle, so I know the other one should be 30. And so we can use the special right triangle rules to figure out what the other side should be. My special right triangle rule said if I have a 30, 60, 90 triangle, then this side's x, this side is x times the square root of 3, and this side should be 2x. Well, I know that 2x is corresponding to 1 again, so I get 2x equals 1. So then I would have x is equal to 1/2. And then basically I could fill in the other sides. We get 1/2 on this side, and we get square root 3/2 on this side. Okay, so I'm pretty much done. So I'm going to say this point here, x comma y, we get the point x comma y. Well, the x coordinate should be how far left we go, right? So we get x comma y should be equal to 1/2 comma square root 3/2. Does anybody see a problem with my solution? In the end, I found that xy, the point xy should be 1/2 comma square root 3/2. Yeah, that's right. It should be negative. Okay, so this is one thing we have to be a little bit careful with. Okay, just because the lengths of the sides of my triangle are always measured in positive because, well, length is a positive measurement, I do have to be careful that when I'm describing a point on the unit circle, although this length is 1/2, then the corresponding point will be negative 1/2 because it's 1/2 to the left. And this length here is square root 3/2. However, since it's a length of square root 3/2 which goes in a negative direction, the point will be negative 1/2 comma negative square root 3/2. Okay, so this is wrong. We don't want to fall into that trap. Okay, when we're on a negative part of the circle, we should think, well, this is in the third quadrant. This is in quadrant 3. Points in quadrant 3 have negative values for the x coordinate and the y coordinate. Okay. All right. So that's it. Finish that example. I think we'll stop there for today, and we'll pick this stuff up next week. I'm a tiny bit behind, but that's okay. I want to make sure we get this basic stuff down well before we move on. Okay, so if you have any questions, feel free to hang out for a little while after class. Otherwise, have a great weekend. I hope you have a restful wellness day. I hope it improves your sense of wellness. And yeah, have a good one, everybody. Thanks, Heidi. You too.